Hello everyone, my name is ILMA HUSSAIN. I am in 6th semester regular. My roll number is 225040 and my university roll number is 22103840101117, and my topic for presentation of differential geometry and tensor algebra is dual space, contravariant, covariant and mixed tensor and their order and type. So let's begin. Before knowing dual space, we must know what is a vector space. So for vector space, let V be a given set and its elements are called vectors. So V is a set of vector elements, and let F be a field whose elements are scalar. F is a field whose elements are scalar. Then we say that V in bracket F is a vector space if it follow the following conditions. These are some conditions. If vector space VF follow these conditions, then it will be a vector space, otherwise it will be not. So firstly, there are basically two conditions. First is that V under vector addition should be a abelian group, and second, there should be scalar multiplication. So there are some certain conditions for a group to be abelian. Now let's see that. So first, there exists internal binary operation plus on V called vector addition such that V comma plus is abelian group. That is, for abelian group we will see certain conditions. First is, for every alpha comma beta comma gamma belongs to V, alpha plus beta in bracket plus gamma is equals to alpha in bracket beta plus gamma. This is also called associative law. Second condition is, there exists 0 belongs to V. 0 is the identity element or 0 vector such that alpha plus 0 is equals to 0 plus alpha is equals to alpha, such that for every alpha belongs to V. This is called existence of identity. Third condition is, for every alpha belongs to V, there exists beta belongs to V such that alpha plus beta is equals to beta plus alpha is equals to 0, which is identity element or 0 vector. This condition is also called existence of inverse. Last condition to be an abelian group is, and the most important condition is, for every alpha comma beta belongs to V, alpha plus beta is equals to beta plus alpha. This is called the commutative law, and the rest of the condition, that is associative, existence of identity and existence of inverse, they are found in group also, but if there is commutative law, then it will be a abelian group. Now for second condition, there exists external binary operation called scalar multiplication. First condition is, for every alpha comma beta belongs to V, lambda belongs to F, that is field of scalars. So lambda bracket में alpha plus beta is equals to lambda alpha plus lambda beta, that is we will multiply this and in between there will be a plus sign. Second condition is, for every alpha comma beta belongs to V, lambda and mu belongs to F. So such that lambda plus mu into alpha is equals to lambda alpha plus mu alpha. There is multiplication, this into this and this into this. Third condition and last condition to be scalar multiplication is, mu lambda into alpha is equals to lambda into mu alpha. And last condition is, that is identity element in scalar multiplication is, 1 alpha is equals to alpha. 1 is the identity element. So if vector space follows all these conditions, then it will be a vector space. Now we have seen what is a vector space. Now we will come to our topic, that is dual space. Let M in subscript M in bracket R be a space of contravariant vectors. Let mu be a function such that MM maps to R such that for all lambda comma mu belongs to MM, then alpha A comma B belongs to R. So the condition would be mu into A lambda plus BV is equals to A mu lambda plus B mu V. Then we say, if this condition is satisfied, we say mu is real valued linear function in MMR. Now let MM asterisk be set of all such real valued linear functions, we define vector addition on mm asterisk as follows. For all mu comma delta belongs to mm asterisk, then lambda belongs to mm, such that mu plus delta into lambda is equals to mu lambda plus delta lambda. This will be our first equation. Now to prove the scalar multiplication between mm and r, that is for all mu belongs to mm asterisk, lambda belongs to mm and a belongs to r, such that a mu lambda is equals to a mu lambda. Here a mu is in one bracket and lambda is in one bracket. Here only lambda is in bracket, that is they are all in scalar multiplication. This will be our equation 2. So from equation 1 and 2, it is evident that mm asterisk r is a vector space under addition and scalar multiplication. Since we have already seen the conditions to be followed for vector space, we can see here that dual space is also a vector space from equation 1 and 2. So we call mm asterisk r dual space of mm r, that is for contravariant. This is the dual space. Now for our last topic, contravariant tensor, covariant tensor and mixed tensors, we must know certain terminologies, that are indices and types of tensor. So let's start. So firstly, what are types of indices? Indices are of two types, that is upper index and lower index. Upper index is also called superscript, that is written on top of the letter, that is subscript. We denote the subscript as upper index, and lower index is also known as a subscript. It is written as below the letter. Now types of tensor. Tensor are of three types: covariant, contravariant tensor, covariant tensor and mixed tensor. Mixed tensor is basically the mixture of contravariant and covariant tensor. So we can also say that tensor are of two types and mixed tensor is a subtype of contravariant and covariant tensor. So what is a covariant tensor? A covariant tensor has only lower index. So if a tensor given has only lower index, that is only subscript, then it will be a covariant tensor. Example is AI, ABI, BI, AIJ, BKLM. So we can here see KLM, all are in subscript. Therefore BKLM is covariant tensor. Second is contravariant tensor. A contravariant tensor has only upper index. Upper means superscript, that is on top of the letter. So example are AI, BI, ABI, AIJ and BKLM. Here we can see in each example all the indices are in superscript. So if indices are in superscript, then it will be a contravariant tensor. So now we have seen covariant tensor and contravariant tensor. So the mixture of these two will be a mixed tensor. Mixed tensor, it has both upper and lower indexes. Example A superscript I, subscript J. Chronicle delta, this particular is known as chronicle delta. We will see next in examples. This is chronicle delta, superscript I, subscript J. B superscript IJ and subscript K. There can be number of indexes. So another example is BIJ KM, AIJ KLM. So these were the examples of mixed tensor. Now we will see order of tensor and the type of tensor. So it is order of the tensor is defined by its index type. जो इंडेक्स का टाइप होगा that will tell us the order of the tensor and type of the tensor. So we have already seen that contravariant tensor में upper index होती है, तो we will denote that by P. Covariant tensor has lower indices, so we will denote that by small q. So for type of tensor, we will in general formula we can say is type of tensor is P comma Q, that is number of contravariant indices and number of covariant indices. मतलब P is contravariant order and Q is covariant order. So this P comma Q will tell us the type of the tensor. For rank or order of the tensor, we can write the general formula as P plus Q. So P means contravariant order plus Q, that is covariant order, will tell us the total rank. Now we will see some example based. For example, we have first example, A superscript I is contravariant tensor, and we know that B subscript I is a covariant tensor. So the question asks us that A I into B J is of type. So we have to tell the type of this particular tensor. So let us see. A superscript I, this part is contravariant, and B subscript J, this part is covariant. Then we will count the number of superscript, that is 1, and number of subscript, that is also 1. So for type we have to write P comma Q. Our P is also 1 and Q is also 1. So the type of this tensor is 1 comma 1 tensor. And for order or rank of tensor, we add P plus Q. So 1 plus 1 is 2. Therefore the rank of this tensor will be 2. Another example is Kronecker delta, that is delta ij. So here we can see P is 1, that is only one superscript, and Q is also 1, that is one subscript. So it is also a 1 comma 1 type of tensor, and rank of this tensor will be 2. Another example is A ij B k l. So we have to tell the type and order of this tensor. For type we count the number of p's. So 1, 2, there are 2 superscripts, so 2, this is our p. And in Q, for Q we have to count the number of subscript. So K, L, these are the 2 subscripts. So this is Q. So 2 comma 2, that is P comma Q is the type of this tensor, and for order we have to add P plus Q, that is 2 plus 2 is equals to 4, that is the order of this tensor. Thank you.